Don't think about it, let's go and solve it. Listen to this video, sing oh hey yo. Just follow these steps, yes explore each step. Anyone can do it, sing oh hey yo. Show the world you hold the knowledge. Feel the formulas and numbers. Show the world what you can do. Prove to them you like it too. I believe in you, but you feel better when you solve it. Yeah, yeah. You better analyze it. Yeah, yeah. Goodness of business, I bet you will learn from this video. Yeah, yeah.
Welcome to Matriculated Channel,
The channel
where
ideas will be
cultivated.
Hello everyone, let's learn together. Are you ready? Let's get started. What is a chi-square test of goodness of fit? A chi-square goodness of fit test is a type of Pearson's chi-square test. It is a statistical hypothesis test used to determine whether a variable is likely to come from a specified distribution or not. It is often used to evaluate whether sample data is representative of the full population. Also, this is a test of difference between the observed frequencies and the expected frequencies. In chi-square goodness of fit test, sample data is divided into intervals. Then the number of points fall into the interval are compared with expected number of points in each interval. Using the chi-square goodness of fit test, you can test whether the goodness of fit is good enough to conclude that the population follows the distribution. Before we perform chi-square test of goodness of fit, we have to check different assumptions. First, one categorical variable per test, either nominal or ordinal. Second, independence of observation. It means that there is no relationship between any of the cases. Third, the group of the categorical variable must be mutually exclusive. And lastly, at least 5 expected frequencies in each group of your categorical variable. So, how do we use chi-square test of goodness of fit? We use the formula x squared is equal to the summation of the quantity squared divided by e, where x squared is the chi-square test, O is the observed frequencies, and E is the expected frequencies.
To perform a chi-square goodness of fit test, follow these 5 steps. First, set up the hypothesis for chi-square goodness of fit test. In chi-square goodness of fit test, the null hypothesis assumes that there is no significant difference between the observed and the expected value. In chi-square goodness of fit test, the alternative hypothesis assumes that there is a significant difference between the observed and the expected value. Second, determine the statistical test to be used. Third, set the level of significance of alpha level. Fourth, perform a statistical computation. And fifth, make a statistical decision and draw a conclusion. Hypothesis testing in chi-square goodness of fit test is the same as in other tests like t-test, ANOVA, etc. The calculated value of chi-square goodness of fit test is compared with the table value. If the calculated value of chi-square goodness of fit test is greater than the table value, we will reject the null hypothesis and conclude that there is a significant difference between the observed and the expected frequency. If the calculated value of chi-square goodness of fit test is less than the table value, we will accept the null hypothesis and conclude that there is no significant difference between the observed and the expected value.
Now, let's have some sample problem to test our knowledge. Suppose you have a die that you are curious if it's fair or not. If it is fair, then the proportion for each value should be the same. You need to find the observed frequencies, and to accomplish this, you roll the die 500 times and count how often each side comes up. The data is in the table. Do the data show that the die is fair? Test at the 5% level. use this table as observed frequencies of dye. In this table, we have dye values from 1 to 6. In dye's value number 1, the observed frequency is 78. In number 2, the observed frequency is 87. In number 3, the observed frequency is 87. In number 4, the observed frequency is 76. In number 5, the observed frequency is 85. And in number 6, the observed frequency is 87, the total of 100. Step 1. State the null and alternative hypothesis. The null hypothesis is the observed frequencies are consistent with the distribution for fair dye, the dye is fair. In the alternative hypothesis, the observed frequency are not consistent with the distribution for fair dye, the dye is not fair. Step 2. Set the level of significance and degrees of freedom. As stated in the problem, the level of significance would be 0.05. To compute for degrees of freedom, we have to use the formula degrees of freedom equal k minus 1, where the k represents the number of population. Therefore, it will become degree of freedom 6 minus 1 equals 5. Step 3. Test statistic to be used. Our test statistic to be used in this problem is none other than test of goodness of fit, since the problem focused on testing the specific pattern of frequency distribution.
Step 4. Compute the statistical value and critical value. First, we have to compute for the expected frequency by dividing the total observed frequencies to the number of sample space of rolling a die. Hence, we came up to this formula. Expected frequency is equals to summation of observed frequencies divided by n is equals to 500 divided by 6. Hence, the quotient 83.33. Now we're ready to compute for the test statistic. It is easier to calculate the test statistic using a table. First, we need to plot the given observed frequencies in the table in the first column. Next column would be our expected frequency that we have computed earlier, which is 83.33. In the third column, we will deduct the observed frequency to the expected frequency. Thus, it resulted to as follows: negative 5.33, 3.67, 3.67 as well, negative 7.33, 1.67, and 3.67. Now, we will square each difference we get in the third column, which it will resulted to 28.40.4089, 13.4689, 13.4689, 53.7289, 2.7889, and 13.4689. For the final column, we will divide the squared values to the expected frequency. Thus, we will get 0.34, 0.16, 0.16, 0.64, 0.03, and 0.16. We will now get the summation of the values to get our test statistic, which is x squared is equals to 1.50. Now, it is time to get the critical value. Using the chi-square distribution table at 0.05 with a degree of freedom of 5, the critical value is 11.07. Step 5. Make a statistical decision and draw a conclusion. Now that we have computed the test statistic and get the critical value, we can now make a decision and draw a conclusion. Since the computed value is less than the critical value, therefore, we have to accept the null hypothesis. Hence, there is no sufficient evidence that the observed frequencies are not consistent with the distribution for fair dye.
Now let's work with the example of the chi-square test for goodness of fit. In the 2000 US Census, the ages of individuals in a small town were found to be the following. We found out that 20% of the people were less than 18 years old, 30% were between 18 and 35, and 50% were greater than 35. So those are our population proportions. That's the distribution of ages we would expect to find in any given sample. Now, in 2010, the ages of 500 individuals were sampled. Below are the results. We have 121 people who are less than 18,
288 that are between 18 and 35, and 91 that are greater than 35. Using alpha point 0.05, would you conclude that the population distribution of ages has changed in the last 10 years? So we have our expected probabilities and we have our actual observed values here. So based on these expected values, if we took a sample of 500, what would you expect the observed values to be? Well, if you expected 20% of those 500 people to be less than 18, you would expect 100 to be less 18. You would expect 150 to be between 18 and 35, and you'd expect 250 to be greater than 35. So that we have what actually occurred in our sample of 500 and what would be expected to have occurred in our sample of 500. And now we can do our hypothesis test for chi-square test for goodness of fit. Step 1. State the null and alternative hypothesis. For the H sub O or null hypothesis, the data meet the expected distribution. For the H sub A or alternative hypothesis, the data do not meet the expected distribution. Step 2. Set the level of significance and degrees of freedom. Alpha is going to be 0.05 just like always. Calculating degrees of freedom is done like this. We just take the number of groups we have and subtract 1. Here we have 3 groups, 18, 18 to 35, and 35. So we just take 3 minus 1 and get 2 degrees of freedom.
Step 3. Our test statistic to be used in this problem is none other than test of goodness of fit, since the problem focuses on testing the specific pattern of frequency distribution. Step 4. Compute the statistical value and critical value. Calculating the test statistic for chi-square is actually not that bad. It follows this equation right here where we take every observed minus expected, square it, divided by expected, and then add everything together so it looks something like this. For less than 18, we observed 121 and we expected 100. So it's 121 minus 100 squared divided by 100, and then we add the other 2 observed minus expected fractions to get our total chi-squared, which is 232.494. We have this chi-square table right here where we look up for the alpha point of 0.5 and the degrees of freedom is 2, and we find 5.99147. Step 5. Decision. So we say if the chi-square that we calculated is greater than 5.99, we're going to reject the null hypothesis. And we can say that the ages of the 2010 population are different from those expected based on the 2000 population. The sample that we observed was different from the sample we expected to find using the chi-square test for goodness of fit.
When you finally know, you understand the topic, cause you listen to this music, sing oh, oh, cause you're confident, babe, you're running this way. We knew that you could do it, sing oh, oh, show the world you have the knowledge. Fill the formulas and numbers. Show the world what you can do. Prove to them you like it too. I believe in you, but you feel better when you're solving. Yeah, yeah. You better analyze it.